This video is about making a titration curve given this information. So there's some strategies here. One is find the most important parts. So pH is 0 at the endpoint and at a perfect buffer. Then we can pick other points as we go. So what I'm going to do is I'm going to do these 1 and 0. Now, there's one thing that's not implicit here is that you kind of have to have a solution of KHP before you titrate it. So what I'm going to say is I added this 0.3 grams of KHP to 20 mils of water. And if I do that, this is what happens. I'm going to go ahead and say 0.00147 moles, and that's the moles of KHP. If I divide that by 0.020 mils, let's say, I'll get 0.0735 molar. And that's what I'm going to start off with. Okay, so in this exercise, what I'm going to do is I'm going to use, instead of writing KHP all the time, I'm going to say HA, so I can figure out where that H is going. And so that's typical for any weak acid, and this is what we're going to do. And this produces A minus and H3O. So I'm going to start with 0.0735 here, 0 here, 0 here. So if I do a rice table, it's going to be minus X, X, and X. Okay, we know that we're going to assume that this X is pretty darn small compared to this 0.0375 molar that I just wrote down. So this is how I'm going to set it up. Ka equals 3.9 times 10 to the negative 6 equals, I would go ahead and say x squared, those are my two x's for A minus and H3O, over 0.0735 minus x. And of course, we're going to assume that this x is close to 0, or very, very small. And so x ends up being 5.36 times 10 to the negative 4th molarity. And since this equals my H3O concentration, my pH of that ends up being equal 3.27. So that's going to be our first point. So and now at 0, it's 3.27. Assuming that I start off with 20 mils of my solution. So the second one now, I'm going to go ahead and figure out at the endpoint. At the endpoint, I have to make sure is that all my KHP is used up. So if I start with this, 0.00147 moles. I'm basically going to use some stoichiometry here. I'll say 1 mole of KHP. And that is a 1:1 ratio. Oh, 1 mole of NaOH. Equals 1 mole of KHP. And then I'm going to figure out how many mils of NaOH I have. So it's 0.001 mole, 1 molar solution, and 1,000 mils of NaOH. Okay, I'm going to cross out units. And we'll be left with mils of NaOH. We end up with 14.7 mils of NaOH at our endpoint or equivalence point. Now, this is the tough part. if we look at this again, HA plus H2O, sorry, plus OH minus this time, produce, and it's a one-way arrow, H2O plus A minus. We will do, this is 0.00147 moles, and this is 0.00147 moles. And this will be, start off at 0 here. 0 there. What we'll do is, since this is a perfect buffer, this is the equivalence point, I'm going to subtract this amount all of it. We'll end up with 0 here, 0 here. It's a perfect reaction. And we'll end up with 0.00147 moles here. And so that's what we're going to go by. So at this point, this is what we're looking at. We're looking at A minus plus H2O yields HA plus OH minus. So this is the base because of that. And so we need to find KB. KB for this reaction will look like this. 1 times 10 to the negative 14th, because Ka times Kb does equal 1 times 10 to the negative 14th. And 3.91 times 10 to the negative 6. And that means it's going to be 2.56 times 10 to the negative 9. And that will be our Kb. Now if I set that equal to basically this stuff in water, now these are my x's over here. And so what I'm going to do is say x squared on top, and then put 0.0347 moles, or molar, on the bottom. Oh, sorry. That's not right. It's 0.0424 molar on the bottom. Put it 0.04. I'll tell you how I got that. This molarity came from the fact that we have I'm going to go ahead and put it right here. We have 0.00147 moles of that stuff. And the solution total is 0.0347 mils. Okay, because we've added 14.7 to 20 mils, and that's liters. That's how many liters we have. And that will be equal to this 0.0424 molar amount. And that's where that came from. Okay, I'm going to stop here and then continue with the next video.